Hello everyone. Why is spectral imaging not widely used in the documentation of painted surfaces? Experience has shown that although spectral imaging draws a lot of interest, it is embraced mostly by research laboratories that constantly are developing new approaches and methods. This is due to the fact that spectral imaging requires specialized instrumentation and knowledge. Furthermore, it is a time-demanding technique. Acquisition requires constant attention from its user to ensure correct data collection and requires significant time. Processing and analysis of the data acquired is a longer process that requires knowledge of materials, physics, and computer science. XpeCAM solution was developed to bring spectral imaging in the hands of conservation scientists for their everyday practice. It is a complete solution composed by three main components. Data acquisition is achieved by the first two components. XpeCAM XO2 is the second version of our multispectral imaging camera. To support the wide spectral sensitivity of XpeCAM, we have developed LAMPA, a broad illumination source. Data processing and analysis is realized in a cloud application named XpeCAM Platform. XpeCAM XO2 is a state-of-the-art multispectral camera with a wide spectral sensitivity range, starting at 350 nanometers and reaching up to 1200 nanometers. Within this range, there are 30 bandpass interference filters, of which 6 in the ultraviolet, 14 in the visible, and 10 in the near-infrared range. A 6.4 megapixel very sensitive monochrome array sensor captures the light transmitted by the filters. An autofocus mechanism corrects for all the achromaticity problems of the optical components, ensuring sharp images in all wavelength bands. Camera controls and data acquisition is performed through an application named SpecEye. SpecEye is a user-friendly software application that takes control of the hardware and automation processes. The program starts by requesting the project name referring to the area under examination, as it can be seen in point 1. Various notifications can appear during the process to assist the user regarding what needs to be done, as seen in point 2. Following this simple preparation, automated acquisition can start with a single button click. The full cube is acquired through autofocus and auto shutter functionality. The recorded images are then saved in a structured folder in the computer's disk. Except the automated mode, there is also a manual operation mode that the user can acquire images on demand from the different wavelength bands and camera shutter times. During this manual process, the user interface provides two important tools to assist the user. One is the image saturation indication bar, where the optimal shutter time versus the objective lens iris can be visualized, avoiding dark or overexposed images, otherwise called saturation. 2 is the zoom functionality that brings a window in the center of the screen to magnification of 1, where 1 pixel of the sensor is displayed in 1 pixel of the screen. This allows better image sharpness visualization for best focusing. Control of the filter wheel's position is realized through a normal control button by clicking on the up or down arrow as seen in point 1. For better visualization, when you click in the middle of the control, a wheel-shaped visual tool is presented as seen in point 2. By clicking at any value on the wheel, the related value is selected. Similarly, the sensor's shutter time can be selected from the related control. LAMPA is a hybrid light source that was developed to help the end user avoid carrying multiple light sources when he needs to perform acquisitions in the ultraviolet, visible, and near-infrared ranges. The three different light sources are integrated in one housing, reducing the necessity of multiple setups, cables, and tripods. Light intensity is minimized to fit XpeCAM sensitivity and wavelength band selection. In this way, based on the wavelength band selected, XpeCAM wirelessly communicates with LAMPA and the requested light source is enabled. This approach results in minimizing the irradiation of the artwork with unnecessary light components, keeping surface deterioration to its minimum. LAMPA can also be controlled autonomously from XpeCAM through a remote control or manually from a keypad control with a small LCD screen on the back of the housing. XpeCAM platform has a vision to be the complete management platform of artwork documentation. In its current version, it allows users to document the artwork's condition through selected questions, texts, and pictures. Furthermore, it features automated processing of multispectral imaging data, the analysis of them, as also the automated generation of editable reports. The platform is constantly under development to expand its functionality and capabilities towards the documentation, but also on the social tools for the communication and development of expert groups. When a multispectral dataset is uploaded to the platform, it initiates automatically a series of processing tasks that result in a corrected 3D dataset named Spectral Cube. These processes include image normalization from the light inhomogeneities and spectral responses, and image co-registration between the different wavelength bands. Image co-registration algorithm is capable of correcting for 6 degrees of freedom, including translational, rotational, magnification, and image perception angle. The resulting spectral cube contains information regarding the different layers of the surface, its chemical composition, and the history of interventions that it has suffered. In the present slide, we see an example of a 24 image set in the range between 370 and 1100 nanometers. The first proposed image that is generated after the correction of the acquired dataset is the natural color image of the surface based on the Sony IMX pattern of filters. Following, the ultraviolet reflectography false color UVRFC is the image result from merging the 380, 450 and 550 nanometer wavelength band images. Similarly, the infrared reflectography false color images IRRFC1 and IRRFC2 are the merging result of 550, 650 and 750 nanometers and 550, 650 and 850 nanometer wavelength band images respectively. The IRRFC is a well-known technique performed in the past by conservation scientists using analog cameras, where the blue light was blocked with a filter, enhancing the absorption of infrared light. To match the analog hue representation was not possible due to the different film sensitivities used in the past, so we propose two different IRRFC images that can match with those differences. Furthermore, in our approach, the UV false color image is expecting to present new visual results of interest for the conservation scientists. Following the generation of the spectral cube, the platform is also triggered to start pigment classification analysis. This is achieved through machine learning algorithms that have been trained in a large reference database that is constructed in our premises. This classification process is fully automated and is able to provide for each pixel the most related correlation with the reference database. At the same time, the algorithm presents the percentage of surface coverage for every pigment classified. Of course, the database, as also the algorithms, are in constant development to include more pigments and better classification efficiency. From the classification results, the system also provides a map for each classified pigment and also its overlay on the color image. The overlaid mapped area is shown with an enhanced color in similar hue to allow better visualization. One example is shown in this picture where red minio is overlaid with a bright red color on top of the color image of this surface. All the images that are processed and generated by the platform, together with all the information the user has provided regarding the artwork, are gathered and included in a final report. This is automatically generated and dynamically changed when the user adds more input to the project. From the report menu, the user has the opportunity to visualize or download the report on demand for further processing to deliver it to the client. At the end of the report, in the appendix section, a number of references will be included to support processing and analysis of all the work performed by the algorithms in the platform. Soon, more specialized reports will be included in the platform, like project, diagnosis, and intervention reports. In this work, we have presented the development of a complete spectral imaging solution. The solution is composed by XpeCAM X02, a novel portable multispectral camera, its supporting broadband light source LAMPA, together with an artwork management platform. The platform incorporates cloud and machine learning technologies necessary for fast and easy access of the data and its results. Moreover, XpeCAM platform provides a workspace for the management of all the documentation data of an artwork regarding its condition and or before and after any intervention attempt. In this last picture, you can see XpeCAM solution in action performing acquisitions in Signinum's lab in Portugal. As you can see, the users are chatting, waiting for XpeCAM X02 to finish the acquisition, proving that the automation is doing the work for the end user. I would like to thank all the Spectral team for all their work and devotion that enabled the completion of this XpeCAM solution successfully, and I would like to thank you all, the audience, for your attention.